In this lecture, we will see how to analyze a beam using moment distribution method. Okay. So this is our question. This is a 3-span beam. All the supports are simple supports, and the loading are 40 kN, 60 kN, and 80 kN symmetrical point loads, and UDL on the first 2 spans. Right. So the first thing to do is you have to find out the value of fixed end moments. Okay. So for finding out the value of fixed end moments, you can use WL square by 8 for the UDL and PL by 8 for WL square by 12 for UDL and PL by 8 for finding out the fixed end moment due to point loads, right? So for FEM-AB, there will be two values. One will be WL square by 12 and plus PL by 8, where P is 40 and W is 20 and L is 6, right? So you can do that and find out the value of FEM-AB and FEM-BA. One will be positive, FEM-AB will be negative 90 and FEM-BA will be positive 90. Similarly for span BC, you can use WL square by 12 plus PL by 8, where P is equal to 60 and W is equal to 20 again and L is equal to 6. So you get two values. So FEM-BC is going to be negative according to sign convention, so it is minus 105, and FEM-CB is positive 105, right? Finally, for span CD, it is PL by 8, so 80 into 6 by 8, that will be 60 kN meter. It is the moment. So FEM-DC will be positive 60 and FEM-CD will be minus 60. Okay. So once you have that, the next step is you have to find out the distribution factor. So now let's see how to find out distribution factor. So the method approach here adopted here is that all the joints in this particular problem is considered to be fixed joints. Okay. So in that case, for every joint, for joint B as well as for joint C, the far ends are always considered as fixed, which means that the stiffness of the members beating at these joints can be taken as 4A by L. Okay, now for the span, for the joint B, there are two members meeting, one is BA and one is BC, and both of them are having stiffness 4A by L. Okay, so in order to find out what is the value of distribution factor for span BA, DFBA is equal to stiffness of span BA, which is nothing but 4A by L, so 4A by 6 whole divided by sum of stiffness of both the spans, which is 4A by L for the first span as well as 4A by L for the second span. So 4A by 6 plus 4A by 6, which means that DB is equal to 0.5. Similarly, you can find out DBC also, that is also going to be 4A by 6 divided by 4A by 6 plus 4A by 6, which is again 0.5. Similarly, you can do for joint C also. So joint C, there are two members meeting, which is CB and CD. Both of them are having equal stiffness and equal length, which means that they are having equal stiffness. So for this also the value is K, and for this also value of stiffness will be K. So there are two members meeting at this point C. So DFCB is equal to K by K plus K, which is 0.5. Similarly, DFCD is also K by K plus K, which is again 0.5. Okay. For the simple joints, the distribution factor is taken as 1. So DFAD and AB and DFDC is 1. Okay. So next step, what you have to do is you have to draw the moment distribution table. So wherein you write all the joints at the top, A, B, C, D. Each joint will be having two columns on either side. For the end joints, we will have only one column. Right? For A and D, we have only one column. For interior joints, we will have two columns because there are two members meeting at those joints. Right? So first thing you have to write down is to write down all the distribution factors as per your findings. So for symbol ends A and D, we have distribution factor is 1, and for all other spans we find distribution factor is 0.5, 0.5, 0.5, 0.5. So you note down that. Once you do that, the next step is you have to write down all the fixed end moment as per the sign convention. So we have already found out what was fixed end moments. So according to the sign convention, we wrote down the fixed end values, fixed end moment values here. Okay. Next step, what you have to do is that you have to do the distribution. So what you have to do is at each joint take the unbalanced moment. So here you can see that there is an unbalanced moment of 90 at joint A. So you have to apply an opposite moment which is positive 90 multiplied by the distribution factor, which is positive 90 into 1, it is plus 90. Okay, so this is distribution at joint A. At joint B, if you take sum of these two moments, you get that the value is minus 15. Okay, so minus 15 is the unbalanced moment. So in order to balance that, you have to apply plus 15 multiplied by 0.5. So that will go here. So 0.5 into 1.5, sorry 15, which is 7.5 here, and 0.5 into plus 15, which is again 7.5. Next up, so take the joint C. So 105 minus 60, which is plus 45. So there is an unbalanced moment of plus 45. In order to balance that, we have to apply minus 45 moment at this point C, which is to be distributed equal according to the distribution factor 0.5 and 0.5. So minus 45 multiplied by 0.5, so that will go here, and another minus 45 multiplied by 0.5 will go here, so that is minus 22.5 at both sides. Okay, at final point it is a plus 60, so in order to balance it, we have minus 60 applied into 1, so it's minus 60. So this is a distribution. So with this we have completed our first iteration. Okay, so once the distribution is completed, the next step is you have to do the carryover. So here we have assumed that all the joints are fixed, which means that half of the moment will be carried over to the far end. So half of 90 will be carried over to the far end, half of 7.5 will be carried over to here. Okay, because all the joints are essentially fixed end. So plus 7.5, half of this will go to here, and minus 20.5, half of this will go here. Okay, similarly minus 60, half of this will go here, and 22 minus 22.5, half of that will go here. Now again, if we check, we have some values of moments at each of the joints. Okay, so here we have plus 3.75. So in order to balance it, we have to apply minus 3.75 multiplied by 1. So that will be our distribution again. Here you have to take sum of these two moments. We get something like 34.75. So you have to distribute it as per the distribution factor. So 34.75 multiplied by 0.5 is minus value, come here, minus 34.75 multiplied by 0.5 will come here. Okay, so similarly you have to do at other locations also. So you have to sum here. So if you sum this, you will get a value of minus 26.25. so in order to balance it, we have to apply positive 26.25, and you have to distribute that, so you get equal values here and here. Okay, so again with this line we have completed our second iteration. So every iteration finishes with a distribution. So if you want to do, you can do one more iteration. So in that iteration, the first step will be carry over. So half of all these moments will be carried over to the far end. So this half of 16.85 will go to this place. Half of 3.75 will go to this place, right? So similarly, complete the entire line here. Again, do the distribution. You will get these values. Okay. So once you get all these values, the final step is that you have to sum up all the values in a given column. So you have to sum the column from here to here so as to get the final bending moment, final support moments. Okay, so once you get this final support moment, you can see that BA is plus 121.468. So we have used active anti-clockwise moments are positive, right? This is the sign convention. So it means positive 121 means it is an active anti-clockwise moment. So here the moment is anti-clockwise. Minus 121 means it is a clockwise active moment. So this is minus. Plus 92 means this is anti-clockwise, and minus 92 means it is clockwise. Okay. So with this help, you can find out all the reactions and also draw the bending moment diagram for this particular case. Okay. So when you draw the final bending moment diagram, it will look something like this. The diagram shown here is from stat pro analysis. So all the positive values have been treated as negative and all the negative values is to be treated as positive in this case. Okay. Because stat is having an opposite sign convention by default. Okay. The same problem which was dealt with earlier could have been done with a modified procedure for semblance. Okay, so what we do is instead of considering all the joints as fixed joint, we'll consider the inner joints as fixed and leave the simple end as semblant itself. Okay, which means that when the far end is a simple end, the stiffness is going to be 3i by L, and when the far end is fixed end or inner joint, the stiffness is going to be 4a by 6. So if you consider this particular joint B, the far end of span BA is semblant, which means that this is stiffness for this one is 3ei by L. Okay, and 3ei by L, and if you consider this point, the far end C is an internal joint, which means that it is a fixed end, so the stiffness becomes 4ei by L. Now you have to find distribution factor for span BA and BC according to these stiffness values. Okay, so DFBA is equal to 3a by L divided by 3a by L plus 4a by L. Okay, which will be value is dash 0.469429, and stiffness DFBC will be 4a by L divided by 3a by L plus 4a by L, which will be 0.57. Similarly, you can find for joint C also, where we get DCB is equal to 0.571 and DCD is equal to 0.429. Okay, so here also, when we consider this joint, the far end D is simple end, so it is again 3e by L. Okay, and when B is considered with respect to C, it is an interior joint, which means that stiffness is 4e by L. Okay, now the remaining step is easy normal moment distribution method only, but the only thing is that before proceeding to the actual moment distribution method, we have to release the simple end. Let's see how to do that. So as normal practice, draw the moment distribution table, write down all the joints at the top. Each joint will be having two columns. Okay, write down the distribution factors. So write down the distribution factors here. The first step, then write down all the fixed moments according to sign convention. Okay, the first step to be done is you have to release the wherever symbol ends are there, you have to release the symbol ends. So symbol ends are A and D, so you have to release A and D, which means that what you have to do is, what is the actual FEM at that point, apply exactly opposite moment at that particular point. So minus 90 is there, you apply plus 90, and if you see the far end is a fixed end. So half of this 90 will be carried over to far end. So 90's half is getting carried to this point, which means plus 45 at DE. Similarly, plus 60 is there. So you apply minus 60 at D, and once one minus 60 is obtained, the far end is C, that is a fixed end because it is an internal end joined. So half of 60 will be carried over to here, which means that minus 60 by 2, which is minus 30, will come here. So once you do that, next step is you have to find out the initial moments. Okay. So in order to find out initial moment, what you have to do is you have to add both these rows together, so that you will get this particular line. Okay. So once you go up to here, the next step is you have to do the distribution. So you can see that at simple ends, the values of moments are 0, because then that means that there is no requirement of distribution to be done at this simple ends. However, at this point we have an unbalanced moment of plus 30. So plus 30, in order to balance it, we have to apply minus 30 multiplied by 0.429 will go here. Minus 30 multiplied by 0.571 will go here. Similarly, at this point, there is an unbalanced moment of plus 15. So in order to balance it, we have to apply minus 15 multiplied by 0.571 will go here. Minus 15 multiplied by 0.429 will go here. Once you do that, the far end for this particular moment 6435 is a simple end, so there is no carry over to this place. However, for this moment, the far end is an internal joint, which is a fixed end, which means that half of this will go to here and half of this will go to here. So with this first distribution, our first iteration was completed. Okay. Now we do the carryover step. So we have some unbalanced moment at this joint D. So minus 4.283 is unbalanced moment at D. So I apply plus 4.283 and distribute that according to the distribution factor. So you do the distribution. Here minus 8.565 is the unbalanced moment. So you have to apply plus 8.565 as balancing moment and distribute that as per the distribution factor. So this is another distribution. With that distribution, we comes to end of another iteration. Again, we have 4.89 here. Half of this will go here, and half of 2.446 will go here. So again, to the distribution, we have the third iteration. Once all the iterations are completed, you have to start summing from the first iteration to the last iteration. So you get the values of fixed end moments. So you can note that these values are same as those values obtained earlier. Okay. So you can draw the find other moment values, as well as you can draw the bending moment diagram and find out the reactions. Right. So that's it for today's lecture. Thank you.